Hi everyone, welcome to week 2 of our course. Today we are going to be covering section 6.5 in the book and 6.6. This video is for 6.5, which covers arc length, right? So the past few lectures we talked about two-dimensional shapes, we talked about three-dimensional shapes. So now we're going to talk about how to use integrals and derivatives to get the length of any curve f of x. You could see this has a lot of applications. Two the book gives is if you're at a baseball game, you hit a home run, and you want to know how far the ball traveled, right? That's going to be an application of this. Other applications are going to be, for example, cables on bridges, where they kind of have this U parabola shape. You might want to know exactly how much cable that you're going to need if you are designing this bridge, and you could use this method in order to figure that out. So this, in addition, also has a lot of real-world applications. So I'm going to start by going through how we derive the formula for figuring out the arc length for a curve, and then going through a couple of examples as well. So let's pull up a picture of this. Here we go. So the big idea, and this is something we've been doing for the last couple of lectures, is to take something and break it up into a bunch of different pieces that we can then integrate over it in order to get our answer right. Integration is more or less just adding up a bunch of tiny things, for example, rectangles, in order to get area. So the big thing here is that if we have some curve, and I'm just going to kind of redraw this picture, but a bit more zoomed out. So we have some curve that looks like this. We can approximate the length of this curve just by drawing some straight line between these 2 points. And that's, if we make these 2 points closer and closer together, that's going to give us a better and better approximation for this length of the curve. And what we're going to do is we're going to add up all of these little chunks by integrating in order to get our actual length of the curve. Right, the nice thing about using straight lines is that we have formulas for figuring out the length of a straight line. So in particular, we're going to call this delta x. In general, delta, which is just that triangle symbol, just means a change, right? So this is going to be the change in the x value, and this is going to be our change in the y value. Well, we know that the length of the curve is going to be the square root of delta x squared plus delta y squared, right? This just follows directly from Pythagorean's theorem, a squared plus b squared equals c squared. Now, the problem is we don't necessarily know what this delta of x squared is and delta of y squared. However, this is when some more calculus is going to come into play, and we're going to use derivatives to approximate this. So if you think about it, if we take a derivative in the middle or somewhere along this curve, just in general, what's going to happen is that these two slopes are going to have, these two lines, are going to have parallel slopes. So parallel slopes. Well, the slope of the first line is just given by rise over run, which is delta y over delta x. And we're saying that for some point in between these 2 points, this is equal to a derivative. So this is equal to f prime of some point, we'll just call it a. But the thing is, as we get these x values closer and closer together, this is just going to be exactly the x value we're looking at when this segment is more or less 0 size. So the kind of trick we're going to do, or the technique is kind of a better word for this, that we're going to do, is we're going to take this equation and we're going to divide everything by delta x squared and then multiply the outside by delta of x. the reason we're going to do this is going to leave us with a delta y squared over delta x squared, which we're going to be able to approximate using the derivative. So this right here is actually equal to delta of x integral of 1 plus delta y squared divided by delta x squared. So what we can do is, if we are taking integrals now, we're just going to integrate over all of this, make our delta x's really, really small. What ends up happening is delta x is going to shift to our dx in our integral. This delta y squared, delta x squared is going to shift to f prime of x squared. And so we get that this is just the integral from a to b of the square root of 1 plus f prime of x squared dx. An important thing to note is you want to take the derivative first before squaring everything. So if you square everything first and then take the derivative, you will get a different answer. These a and b are just given values, right? You might want to find the length of the curve from x equals 1 to x equals 4. These will be given for this specific problem that you'll be looking at. So this is going to be our formula that we have for the length of a curve. So let's jump into an example. I have one right here. Oops, I want to be on this page. There we go. So let's figure out the length of this curve. So what this means is that our f of x is going to be x to the 3/2. Our a is going to be our leftmost x value, very similar to the past 3 sections. A is going to be 0, and our b is going to be 4. So things we need for this now is we just need to figure out the derivative of f. So f prime of x is just going to be 3/2 x to the 1/2. I subtracted 1 from 3/2 to get 1/2. So plugging everything into our formula, we get that the length is equal to the integral from 0 to 4 of square root of 1 plus 9/4, so that's where 3/2 squared comes from, x dx. Okay. So in general, when we're doing these types of problems, you'll use one of two techniques in order to figure out the derivative, or the integral, excuse me, of a square root. We'll either use u substitution, which we'll do in this case, or we will try to express whatever is on the inside of the square root as a square. We'll talk about that method next, and this will allow us to simplify. As we move further into the course, we will learn some other techniques for dealing with square roots. Specifically, we'll talk about inverse trig functions, which, if you remember back from Calc 1, have derivatives that involve square roots. In general, though, those are really the only two techniques we have right now for solving these integrals. In general, integrals with square roots tend to be fairly difficult as well. So try one of those two techniques for these types of problems. So as I said before, we're going to use u substitution for this one. U is just going to be inside whatever is the square root. So we have u equals 1 plus 9/4 x. Taking derivatives, we get that du is equal to 9/4 dx. So when we plug in dx, we're going to get 4/9 du. And finally, we also need to change our integral bounds. So we have x equals 0. Plugging this into our equation is going to give me u as 1. And finally, x as 4. Plugging it in, 9/4 times 4 is just 9, plus 1 will give me u equals 10. So this integral then becomes, with all of these substitutions, now the integral from 0 to 10 of the square root of u times 4 ninths, excuse me, du. Okay, square root of u is the exact same as u to the 1/2. So when we take integrals, this is going to be 2/3 u to the 3/2 times 4 ninths evaluated from, oh, excuse me, I made a mistake here. It's hard when I'm not teaching in person. Normally, people will correct me on these types of things. And I may make mistakes in the videos. If you do think I made a mistake, please just shoot me an email or come to office hours. I can see if I can correct it, and I will post something on Canvas about the mistake as well. Especially with these very heavy algebra type problems, it can be really easy to make kind of like simple, sloppy algebra mistakes for these problems. Okay, so moving on, we need to evaluate this 2/3 u to the 3/2 times 4 ninths from 1 to 10. So plugging everything in, we just get that this is going to be 8 over 27 times 10 to the 3/2 plus 8 over 27 times 1. Oh, sorry. Minus 8 over 27 times 1. Minus. Which is going to be approximately, if you plug it into your calculator, about 9.1 units. So if you were walking along this curve right here, at the end, after you reach x equals 4, you would have gone about 9.1 units. Okay, so now we are going to do another example, not particularly much more complicated. However, it's going to use a different technique for solving the integrals rather than use substitution. So the problem that we're going to be doing is this one right here. That is going to be our curve, which is given by y equals, let's see, x to the 3/2 over 3 minus x to the 1/2, or square root of x, right? They're the same thing. Okay, so we also are evaluating this integral from a equals 4, which is not super clear from this picture, to b equals 16. So first step, we need to figure out the derivative in order to plug it into our formula. So f prime of x, derivative of x to the 3/2 is going to be 3/2 x to the 1/2. So this is going to leave us x to the 1/2 over 2 after the 3's cancel. And the derivative of x to the 1/2 is going to be 1/2 x to the negative 1/2. So this is 1 over 2 x to the 1/2, right? Negatives will always put things into the denominator. All right, and now what we can do is we can figure out what f prime of x squared is. So this is square root of x over 2 minus 1 over 2 square roots of x, and then we just multiply it by itself. Square root, it's not liking me writing over here. Well, let me just write it under that. Oh. All right, my pen is now back alive, so we can continue this problem, right? We were trying to figure out what f prime of x squared is, so we are just taking this and writing it out as the square root of x over 2 minus 1 over 2 square roots of x. We can FOIL this out. The first term is going to give us an x over 2, multiplying the square root of x over 2 times negative 1/2 over the square root of x will leave us with minus 1/4. The inside terms will have the exact same thing of this minus 1/4. Oh, excuse me. This first term should be x over 4, not x over 2, because we have 1/2 times 1/2. And then finally, the last term will be plus 1/4 over x. So taking all of this information, plugging it into our equation, we get that this is the integral from 4 to 16 of the square root of x over 4 minus 1/2 plus 1 over 4x. Make the square root a bit longer. 1 over 4x plus 1 dx. So if we simplify this, we can pull a 4 out of everything, or a 1 over 4 out of everything, which is the same as multiplying by 1/2, because we're in a square root. So we have 4 to 16 of 1/2 square root of x. We have a positive 1/2 now. When we pull out the 1/4, that's going to leave us with 2. So x plus 2, and finally plus 1 over 2x, or just, sorry, 1 over x. Still dx. Now, as I mentioned previously, the second technique we have for solving integrals with square roots is we're going to recognize the inside of the square root as something that's actually a squared. So that way the square and the square root are going to cancel with each other. So what this kind of looks like, if you think about it, is what x plus 1 squared is, right? X plus 1 squared is just x squared plus 2x plus 1. And we can see these two things kind of look similar, right? We have the x squared behaving like the x, the 2x behaving like the 2, and the 1 behaving like the 1x. So in particular, if we kind of play around with the numbers, see what we get, we actually get that x plus 2 plus 1 over x is going to be equal to the square root of x plus 1 over the square root of x, all squared. You can FOIL this out yourselves, double check the work. It does actually work out in this case. And we do get that that's what this is equal to. So we can then simplify this integral farther and get that this is the integral from 4 to 16. Pull the 1/2 outside of the square root of x plus 1 over the square root of x dx. Taking integrals is going to lead us to 1/2 integral of square root of x is going to be 2/3 x to the 3/2, and then this x to the negative 1/2 will become 2x to the 1/2, evaluated from 4 to 16. And so when you plug everything in, we get this is equal to 1/2, 2/3, 16 to the 3/2 plus 2 times 16 to the 1/2, and then minus everything when we plug 1 in, so 2/3, or sorry, when we plug 4 in, times 4 to the 3/2 plus 2, 4 times 4 to the 1/2. All right, we can't forget about this 1/2 on the outside here. We need to make sure that at the end we are multiplying everything by 1/2. So when you go through everything and you simplify out, this is going to be equal to 62 over 3. And that's going to be your final answer. So just coming back to the original problem, this is going to be the distance total traveled if you were to go from this point right here at x equals 4 all the way up here to x equals 16 following this curve. So there aren't these kind of tricks that we were talking about with the solids, so revolving around different axes, The one thing that could possibly come up is going to be functions with respect to y instead of with respect to x. But the nice thing about this is it's going to behave the exact same way. So functions with respect to y. We just are going to have the exact same function of length is the integral from a to b, where these are now y values of square root of f prime of y now squared plus 1 dy. So the reasons you would use this, one case is that you're just given the function in terms of y instead of terms of x, and then you can just plug everything into this formula and it works out. There are very rare cases where the derivative function is not going to work nicely with this square root. If you can't for some reason figure out how to do it, maybe try taking the inverse of the function to get it in terms of y instead of in terms of x, and taking the function with respect to y. That will work sometimes. It tends to be pretty rare that that happens. More commonly, it's just that we have easier functions when we're dealing with these functions with respect to y when they're already given that way. It's the exact same process, so I'm not going to go through another example like this, but it is a good thing to know that it might come up in worksheets or on a test where you can just take the integrals with respect to y.